Hello everyone, welcome back to Judgment Decision Making. I'm Dr. Padilla. Now we're going to talk about reciprocal altruism. Now in the past few lecture sets, we've seen examples of individual selection where people try to make sure that their genes get propagated, and also kin selection where they're doing the same action but they're supporting the reproductive fitness of individuals that share genes with them. And this begs the question of, is the driving force of behavioral evolution always that someone be vanquished? Is it always the case that you have to stop someone else from reproducing to make sure that you can, or just be indifferent to their reproductive success? And of course, that's not what we see in human behavior. There's many examples of altruism, especially right now. We have examples of amazing people putting themselves and their families at harm to help others with the coronavirus. Healthcare providers, medical specialists are really doing fantastic work right now. We're also seeing some examples of people doing the opposite, where they're taking advantage of this circumstance. So these are some individuals that have set up a pop-up corona testing site that is fake, and they're charging people $240 to get fake corona tests, and they're being shut down right now. But the one I want to focus on for this lecture is reciprocal altruism, the concept of I'll scratch your back if you scratch mine. And we see this in many types of behaviors with animals and also with humans. The geese right now in this picture are organized in a V because they're getting an easier ride from the updraft of the geese in front of them. And the goose that's in front will actually circle out so that it doesn't get as tired. And that's the same way that biking pelotons are organized, where the person in front is doing the most work because of the wind resistance. And if you're on a team, you will cycle the person out in front so that he doesn't get as tired. Now, in terms of reciprocal altruism, there's a variety of conditions that a species needs to have in order to have this type of activity. The first is that the species must be very social. Like humans, we're social. The most species that are social, you'll see reciprocal altruism. Social interactions have to be frequent. You need to have practice doing these types of activities, and individuals must be able to recognize each other. You have to tell if it was actually this person that was altruistic towards you so you can reciprocate. However, individuals often attempt to cheat, to not reciprocate. And this brings up the question, when is it optimal to cooperate and when to cheat? This, of course, brings up this massive field of game theory, which is the study of mathematical models of strategic interaction among rational decision makers. The whole goal of game theory is to model the ways in which decision makers work and cooperate together to identify optimal strategies, which has produced some really fascinating findings that can help us understand how we make decisions. In particular, they've focused a lot on this prisoner's dilemma that we'll learn about in the next slide. It's a concept of what strategy for cooperation is optimal. I'm going to play you this brief video that describes the prisoner's dilemma.
A prisoner's dilemma is a situation described in game theory, a branch of economics that analyzes decisions made under conflict and uncertainty. In a typical prisoner's dilemma scenario, two parties under threat have the option of protecting themselves at the expense of the other party. For example, Chris and Stephen are suspects in a number of robberies. The police are able to detain both men, but the evidence placing them at the robberies is weak. Thus, they need confessions in order to convict either man. During a private interrogation, an officer makes Stephen a deal. If he confesses and testifies against Chris, then he is free to go. However, when the officer talks to Chris alone, he offers him the same deal. If Chris testifies against Stephen, he is free to go. Unbeknownst to either man is that if they both testify against each other, each receives a sentence of 10 years. If one testifies and the other does not, the person who does not testify receives 20 years. And if they both remain silent, each gets 1 year. Without cooperation between the two men, the dominant strategy is for Chris and Stephen to rat each other out, as the possible outcome of 0 to 10 years imprisonment is better than the alternative possibility of 1 to 20 years. A pricing war between two identical firms can also be described as a prisoner's dilemma. where rather than fiercely undercutting the competitor's price to gain market share at the cost of profit, companies cooperating on a set price for similar products can share the margins. Without cooperation, each firm finds it in its own best interest to gain the lead over the other firm.
I really like that video clip because it does a nice job of laying out the context of the prisoner's dilemma and describing how it applies to real-world contexts where different firms are competing against one another. Now I'm going to lay out the different possible outcomes as they relate to how the book was describing them. So in this first outcome, let's say this individual is you and you're competing against one other person. Now let's say both of you refuse to inform on each other. And in that case, each of you would get 1 year of a prison sentence. Let's say there's another situation where each of you actually do inform on each other. You would get 2 years of a sentence. And then the final scenario is where one of you informs and the other one stays silent. Let's say you inform on your competitor and that competitor doesn't inform on you. You would go free and your competitor would get a 3-year sentence. So if you actually know how many rounds of this prisoner's dilemma game that you're going to play, you can figure out the optimal strategy. So if it's just one time, the optimal strategy is actually to defect. Let me lay this out for you. So your sentence would actually average to 1 year if you decide to defect. For example, either you get 0 years because B, your competitor cooperates, or 2, if he defects. That averages out to 1 year. Now let's look at the alternative scenario. If you decide to cooperate, that would actually average out to 2 years, which is more than 1 on average. So you would get 1 year if B cooperates and 3 if B defects. So in this case, when you know the number of rounds, you should always defect. If we look at the same scenario but with 3 years, same outcome where you should always defect. The average sentence if you do defect is 3 years, and then the average sentence if you decide not to defect is 6 years. The question is, what if the number of rounds is unknown? This is where it becomes rather interesting. So I'm going to show you this video of some really fantastic work that was done to compare all of the different types of strategies that you could possibly use, because there are many, many strategies. You could always defect, you could always cooperate, you could cooperate 50% of the time, and there's one particular strategy called tit for tat that seems to be superior.
Robert Axelrod is a political scientist who uses game theory to study human behavior.
The Cuban Missile Crisis happening while I was in college, looking around for something useful to do with mathematics, certainly had an influence on me. I thought, this is nuts that people would be willing to risk hundreds of millions of lives for where these missiles are based when it didn't matter where they were based. I thought, maybe there's something to understand here that isn't obvious. The idea of having people submit computer programs to play a game that's very simple but represents the problem of the conflict between making short-run gains by being selfish and seeking longer-term gains from cooperating with others. So I was surprised when the simplest of all the strategies submitted was the one that did the best.
Known as tit for tat, a player cooperates in the beginning, then does what the opposing player did on the previous move. Axelrod investigated other strategies of cooperation in the real world.
In World War I, they had something on the Western Front called the live and let live system, where the British and French on one side and the Germans on the other would often do things like shoot their artillery between the trench lines, not on the trench lines.
His book, The Evolution of Cooperation, proposed the role of forgiveness in conflict resolution and included a landmark article co-authored with evolutionary biologist Bill Hamilton.
The one important modification is if there's some possibility of misunderstanding, then you should be somewhat more forgiving once in a while.
I also really like that particular clip because it does a fantastic job of illustrating how this mathematical calculation of these best strategies by computer simulations can actually help us understand how people perform in wars, how wars are organized and fought, and how this type of research is motivated by a sincere interest to help society, not just do calculations on computers. So what they propose is this tit for tat plus forgiveness strategy. We focus first on tit for tat. Note that you can never actually win. Best case is a draw. If playing against another person using tit for tat or someone using an always cooperate strategy. So you can't actually win outrightly with this tit for tat strategy. However, other strategies playing against each other can produce catastrophic losses. And when everything is summed, tit for tat wins. Tit for tat has 4 things going for it. One is its proclivity is to cooperate. That is its starting state. So by default, it's going to begin by cooperation, which is a rather nice feature. But it isn't a sucker and it punishes defectors. So it won't always let itself get stepped on if someone is defecting. It's forgiving if a defector resumes cooperating, so will tit for tat. So it's adaptive to the new context of the player state. And the strategy is simple. It's easy to enact. It's easy to enact in your daily life as well. Now, what they noted in the video, just very briefly, but it's detailed very nicely in the book, is that the tit for tat system is a little flawed in that it has issues if there are any type of errors in the system. So it needs to have a forgiveness component if there's some type of miscommunication in the signal. So for example, if you're playing with someone and you're using a tit for tat strategy, you need to account for maybe someone accidentally defecting when they meant to cooperate. And if you add that into the system, you can kind of increase the optimization of it by adding a forgiveness component. And there are a variety of different forgiveness strategies that are included in tit for tat. And I won't summarize them here, but just note that tit for tat does best when it includes a type of forgiveness. Okay, summary here. 3 concepts can explain otherwise puzzling decisions. One is individual selection with competitive infanticide as a canonical example. We learned that in the last lecture. Kin selection, where there's male-to-male aggression between groups in only some primate species. It's also why species have hierarchical ranking systems. And the one we just learned about, which is reciprocal altruism. I'll scratch your back if you scratch mine. Now again, the book goes into a lot more detail about additional complexities to reciprocal altruism. We'll keep it simple for now, but if you're interested, it's there for you to read more and learn about many different examples of reciprocal altruism as well.